Hello. To repair the primary 3-meter linear motion guideways of the surface grinding machine that I'm currently working on, covered in my previous videos, from number 23 to number 30, it is essential to have, as one of the primary tools, a straight edge with appropriate surface characteristics. The dimensions of this reference surface are 1070 mm by 60 mm. From its reference surface, I will transfer an oil-based pigment onto the guideway line being repaired. This video focuses on the key information about how to independently manufacture a highly precise straight edge and maintain its precision geometry throughout its use. The quality of this straight edge, along with measuring instruments, will determine the quality of this repair. It is, therefore, a critical component that directly affects the success and accuracy of the repair. The high precision in monitoring the condition of the machine's guideways is ensured through the use of an autocollimator. Therefore, highly precise straightedges are necessary for scraping. The best solution for me is to manufacture it myself, as I have assembled everything necessary for this in my workshop. This way, I can independently control its quality, specifically, the flatness of its surface, and reduce any geometric errors to the required precision at every stage of work. A surface ground on a surface grinding machine, when interacting with high-precision measuring instruments, shows deviations from absolute flatness. Thus, I will have to further align it. At the final stage of work, its accuracy will be brought to a level where the error is just 1 micron across the entire working surface. Only then will I complete the repair of the linear motion guideways with the desired high precision. After the initial grinding, it is still far from an ideal state. You can currently observe that the dial comparator, microcator, with a scale division of 1 micron, equal to 39 millionths of an inch, mounted on a stand with a support diameter of 130 mm and the same probe extension, 130 mm, shows deviations of about 20 microns during movement. Although this is an indirect measurement, and obtaining precise data from it is challenging, it still clearly indicates that the surface is not perfectly flat. So, I need to create a 1-meter precision straightedge. As previously mentioned, I will use its working surface to transfer black pigment mixed with oil onto the guideway being repaired, scraping away the areas that come into contact. Through repeated execution of this process, the reference surface of the straightedge will be transferred to the guideway under repair, achieving a sufficiently high level of flatness and straightness. My plan is to achieve an error of less than 5 microns across the entire surface of these 3-meter-long linear motion guideways, equivalent to 200 millionths of an inch. I have prepared a workpiece for this straightedge using an I-beam. I could have sourced a cast iron straightedge of similar dimensions, but I chose to make it from an I-beam. This choice makes the straightedge significantly lighter than a cast iron one, allowing me to work alone without an assistant. The I-beam workpiece for the straightedge has been annealed to relieve any internal stresses. After annealing, the workpiece was ground on a surface grinding machine. The workpiece has also been reinforced against transverse bending with an adhesive inserted stiffener. The decision to add this insert was made after annealing, which made the process more complicated. Ideally, such reinforcement would have been installed by welding, followed by annealing to relieve stress, but that wasn't the case here. The stiffener was glued in place, so I relieved the assembly of torsional stresses during the adhesive curing process. However, even after the surface grinding machine, this is far from being a precision straightedge. The surface grinding machine I have access to is not precise enough for this workpiece to qualify as a reference straightedge, as is the case with most surface grinding machines. In most cases, after processing on a surface grinder, especially if the machine has been in service for decades, the resulting surface is not flat enough to meet the accuracy standards for a straightedge. Even if the surface grinder isn't worn out, the typical accuracy for a surface 1070 mm long is around 0.01 mm, which is the standard tolerance for a new surface grinder but insufficient for a straightedge. With such a straightedge, it would be impossible to achieve precise linear guideways after their restoration through scraping. Even if I had access to ultra-precise grinding equipment, I would still need to periodically inspect the straightedge's surface geometry. During its use, various impacts could potentially alter its geometry, and as I perform the restoration, I must be certain of its perfect flatness. Even after the surface grinding machine, this is far from being a precision straightedge. This inspection is particularly critical during the final stages of scraping. In this video, I will perform a geometric inspection of the surface. I've dedicated this video to the measuring process because it is a crucial step in crafting this or any similar straightedge. I will measure the surface produced by the surface grinding machine and create a map of its topography. This map will show where and by how much, with very high accuracy, down to 1 micron, the surface deviates from perfect flatness. This procedure, as mentioned earlier, is key to the straightedge creation process. Subsequently, based on this measurement data, I will process the surface, removing excess metal from higher points as needed. As a result of this process, with periodic inspections using similar measurements, the surface will become even, and its deviation will fall within the desired range for the task at hand, reaching a precision of up to 1 micron in the final stage. With some experience, it is not difficult to lower the high spots, knowing their locations and heights, gradually approaching an ideal flatness. Metal can be removed using a scraper, sandpaper, or a Dremel tool. Lapping is also applicable. I've prepared an animation for this video. Measuring dimensions within tens of microns on a plane like this, about a meter in length, presents a psychological challenge due to the lack of natural perception. Such a small linear dimension is beyond our ability to perceive visually or tactually. The surface appears completely flat, making it difficult to grasp, contrary to our natural instincts, that bumps and hollows are indeed present, albeit with heights or depths measured in microns, which our natural senses cannot detect. Yet, in this case, we are working precisely with these minuscule dimensions, which hold the key importance. This creates a perception issue and some discomfort since we are used to seeing what we are working with. Here, this condition is not met, the plane seems perfectly flat, and only the instruments reveal the presence of bumps and hollows. Animation effectively addresses this visual perception problem. This is how our eyes see the surface, and this is how the instruments see it. It may seem like a flat surface, but the sensitive micron comparator tells a completely different story. This video is quite complex and rather lengthy. It took me over a month to edit it. I apologize for the delay. I hope to release new videos more promptly in the future, as I have plenty of recorded footage and more than enough topics for upcoming videos. We can conditionally amplify the scale of dimensions deliberately in just one vector, the one we are working with. If we apply such one-sided magnification, say 5,000 times, as has been done here along the vertical axis relative to the others, we can clearly see this micro-relief. This is exactly how I perceive this relief, clearly defined, when using a microlevel and corresponding calculations to construct a topographic map of the surface. Guided by this map, I will scrape down the higher areas of the surface and then repeat similar measurements. Scraping or removing a very thin layer of material is not particularly difficult, especially if you have some skill. Then, after scraping or removal, a new map with the current topography of the surface needs to be created. After about 10 to 15 such events conducted consecutively, I will achieve a perfectly flat surface where the height difference between the highest and lowest points will be less than 1 micron. But first, let's create an initial topographic map of this surface and examine its current profile. This, as previously mentioned, forms the focus of this video. Understanding this task makes it easier to grasp how to achieve a reference level flatness. There was an instance where I needed an accurate method for such measurements, and using the resources available at that time, I devised this technique. I assembled a stand similar to this one and, using my precision spirit level, which I had already made, carried out the task and achieved the desired result. These recordings, over 3 years old, from 2021, have preserved video footage of that work. Back then, it was my first experience creating a precise straightedge 1 meter long. Let's return to the structure of the measurement stand. I recommend watching my video number 23, where I explain this stand in detail. Here's the link. I hope you've already watched it, and now I'll continue discussing the core topic. First, I prepare the surface to interact with the precision feed of my highly accurate bubble level. Video number 3 on my channel is dedicated to the construction of this instrument. The surface must be clean and lubricated with graphite. Without graphite dust as a lubricant, the interaction between the feet and the surface is less efficient, which introduces minor inconveniences during instrument movement, ultimately affecting measurement accuracy. I haven't found a more effective lubricant than graphite dust. Without it, the process is significantly worse. I extract graphite from a pencil. Next, I place a very flat steel bar, which I previously lapped, onto the surface of the bridge. My movements are extremely cautious to avoid microdents on the surface of the straightedge or the bar itself. With this bar, I rub in the graphite dust. The dust must be finely ground enough not to influence the readings of the highly sensitive bubble level when it's on the measured surface. Simultaneously, this bar slightly smooths out the surface after grinding on a flat grinding machine, as the entire surface, when viewed under a microscope, consists of microscopic scratches. After preparing the surface, I place the bubble level. The level's precision feet now glide smoothly and softly over the surface. As I've noted several times before, the surface, when considering the microscopic dimensions measured by the bubble level, the dimensions critical to this project, is uneven. For measurements, I create a grid of points on the surface where the height will be measured. These points are chosen arbitrarily, but I consider the distance between the left and right precision feet of the bubble level and ensure the density of these points is sufficient to gather enough data for the project. After creating a grid of measurement points, I determine the location of the reference points for these measurements. Reference points are 3 points chosen from those marked on the diagram. They lie in an imaginary ideal plane, and their height is considered 0. I select these points arbitrarily, and in my opinion, it's more convenient when they are closer to the center. Here is the version I selected. To simplify the presentation of the material, we will adopt a set of designations and terms. An arbitrarily chosen grid of measurement points, where each point is given a conventional name. Arbitrarily chosen measurement lines, in this case, 2 lines are sufficient, and we will name them A and B. The imaginary ideal plane, alpha. Control microcaters and transverse microlifts, K and L, and the longitudinal microlift, M. The surface being measured. The microlevel. The feet of the microlevel. The central position of the microlevel bubble, i.e. when the bubble is precisely at the center of the scale. The microlevel base, 280 mm. The microlevel base, 140 mm. The microlevel base, 60 mm. With all the necessary elements in place, equipment and a plan, we can proceed with the first round of measurements. This is how the process of shooting this segment actually unfolds. In the future, the viewing angle will be limited to ensure the scales and instrument readings are clearly visible. I very carefully place the microlevel with the 280 mm base on the prepared surface to be measured. Even a minor impact could leave a microscopic but undesirable dent on the surface. The surface interacts well with the microlevel's feet, allowing smooth and stable movement. The movement of the precision level across the measured surface is smooth. I can tell by the sound and feel it tactily. I position the feet of the microlevel on points A4 and A6. Using microlift M, I adjust the bubble to the central position. Now, I align points A4, A6, and B4 by controlling microlifts K, L, and M, positioning them relative to the Earth's center of mass so they form the imaginary plane alpha, which will serve as the zero level for this measurement. Next, I move the left foot of the microlevel from point A4 to point B4 while keeping the right foot on point A6. The bubble moves very slowly, and each measurement requires a long wait for it to settle. By adjusting microlifts K and L, I ensure that the measured surface, relative to the Earth's center of mass, maintains the bubble in the central position in both the first, A4, A6, and second, B4, A6, positions. In this case, microlift K needs to be lowered, and microlift L raised by the same amount to minimize any influence on the longitudinal inclination reflected by microcator M. This alignment of the measured surface will take considerable time, roughly half an hour, as it requires numerous adjustments and waiting for the bubble to stabilize. However, I will only show the final adjustments to save time. Once the surface is aligned, I set all 3 microcator's needles to the 0 position on their scales. This ensures constant monitoring of the surface's stability between microlifts K and L, confirming the accuracy of the measurements. Microcator M will then serve as the tool for collecting data on each measurement point according to the scheme. To keep this setup as simple as possible, I adjust the microcator's positions in a straightforward manner. They are not clamped fully rigidly in their mounts, allowing me to rotate them slightly around their axes to raise or lower them. At the same time, they are secured enough to function correctly. All components of this measurement setup are readily available and, despite their simplicity, perform their tasks effectively. For example, a small piece of glass glued to a bracket interacts well with the microcator's probe, providing the necessary data. The bracket itself is attached to a straightedge with a simple clamp. A micrometer indicator with 0.001 mm sensitivity is precise enough for this system. It's not exactly cheap, but at the same time, it's reasonably priced on the secondary market. And it functions brilliantly. I have a video about micrometer indicators on my channel, and I recommend watching it. The micrometer's plunger applies minimal pressure on the support surface, so the plunger's foot is only lightly clamped. This light clamping is sufficient to secure the micrometer, while still allowing me to slightly adjust its position. By rotating the plunger and the clamps and applying slight force in the desired direction, I can move it up or down as needed. As I mentioned earlier, the measured plane is precisely aligned to the Earth's center of mass only transversely, i.e. between microcators K and L. Longitudinally, measurements will be performed by adjusting microlift M to center the bubble on the scale for each point in the scheme. Thus, we are only close to a precise alignment with the Earth's center of mass in this direction. If desired, it is possible to align the plane precisely to the Earth's center of mass even between reference points A4 and A6, but this is unnecessary. Being close to this state is sufficient. As you can see, after rotating 180 degrees, the bubble shifted slightly to the left, approximately within the range of the measurements themselves. Now, the bubble is back in its central position. I confirm that everything is zeroed and functioning correctly. The bubble is in the central position, and points A4 and B4 are at the same height. I mark the 0 points A4, B4, and A6 on the diagram. Next, I measure the position of point A8. The bubble shifted slightly to the right, approximately by a third of the scale division. Lowering microcator M's probe by 5 microns, 197 millionths of an inch, brought the bubble back to the central position. The distance between points A4 and A6 is 280 millimeters, while the distance between the support axis of microcators and microlifts K and L, where my straightedge pivots, controlled by microlift M and microcator M's probe, is 830 millimeters. Thus, the formula is derived. We take x as the amount by which point A6 must be lowered to bring the bubble to the central position. So, 830 mm divided by 280 mm equals 5 microns divided by x. Therefore, 2.96 is equal to 5 microns divided by x. Thus, 5 microns divided by 2.96 equals x. This means x equals 1.7 microns. Point A8 is above the imaginary plane alpha, which includes points A4, A6, and B4, by 1.7 microns. Thus, the position of point A8 relative to the imaginary plane alpha is now known and expressed as a linear dimension of 1.7 microns, or 0.017 millimeters. After measuring point A8, I returned point A6 to the imaginary plane alpha. I want to emphasize that the measuring points A4 and B4 must always lie on a straight line parallel to plane alpha. This is confirmed by microcator K and L, as their needles remain in the 0 position. When I adjust the tilt of the measured surface, centering the bubble using microlift M, the straight line between points A4 and B4 shifts slightly relative to plane alpha but remains parallel to it. While resetting A6 to the alpha plane isn't strictly necessary, it helps me better estimate the direction and degree to adjust microlift M for the next measurement. I'll demonstrate these actions using animation. Here are 3 0 points, B4, A4, and A6, aligned with the imaginary plane alpha. Placing the precision level on points A6 and A8, I tilt the measured surface so that the bubble occupies the central position. If we hypothetically lower the imaginary plane alpha by the corresponding amount, it will align with points A6 and A8. In this position of the measured surface, I record the readings of micrometer indicator M. After completing the measurement of point A8, as I mentioned earlier, I return the measured surface of the straightedge to its original position by raising its right side back by 0.005 mm. The needle on micrometer indicator M is now back in the 0 position. This prepares me for the next measurement. Essentially, I reset the measured surface to its original state before the next measurement. As expected, the bubble moved out of the central position. I then move the microlevel to points A2 and A4. Let me remind you that point A4 is at 0, it lies in the imaginary alpha plane, which serves as our reference height. The bubble position will indicate whether point A2 is higher or lower relative to the alpha plane. By adjusting microlift M, we center the bubble on the scale. Microcator M will then show the linear displacement of its probe, and using the formula, we can determine the position of point A2 relative to the alpha plane. On points A2 and A4, the bubble noticeably shifted to the right. After determining that lowering microcator M's probe by 46 microns, 0.046 mm, would return the microlevel bubble to the central position, I made the adjustment. It took about 30 seconds for the bubble to slowly stabilize in the central position. Now it is known that the measured point A2 is 15.5 microns below the imaginary plane alpha. I then reset the measured plane to its original state and verified the repeatability of the measurements by placing the microlevel in the initial position, A4, A6. The bubble should return to the central position. This happened as expected, confirming the accuracy of the measurements. The repeatability of measurements is the most important criterion for measurement quality. The variation in the readings of measuring instruments during multiple repeated measurements at each position will inform you about the actual degree of measurement accuracy. The position B4, A6 also confirmed the accuracy. Here too, the bubble stayed centered on the scale, as it should. Therefore, the positioning conditions for the measured surface are fully met. Since moving the microlevel across the measured surface applies forces to it, and the microlevel's weight is a force, I constantly monitor the microcator's needles, especially those of K and L, to ensure the measured surface's spatial position relative to the Earth's center of mass remains unchanged. This condition alone justified building this setup. Even if I had been satisfied with less precise readings of the feet's upward or downward movement directly from the microlevel's vial, it would still be crucial to ensure the surface's spatial stability, which this setup successfully achieves. It is worth noting, and this is a key point, that the scale of the microlevel ampoule allows for very precise centering of the bubble, achieving micron-level accuracy over a meter distance. However, reading slope values directly from the ampoule scale with such precision is unlikely. The positions of points A2, A4, B4, A6, and A8 are now known. I now proceed to line B. I measure point B6. Naturally, the process is the same, so I won't show the further steps. I will note, however, that after completing the measurements using the 280 mm microlevel base, I used the 140 mm base to scan intermediate measurement points. It would have been entirely possible to conduct these measurements using only this single microlevel base, 140 mm in size. However, I believe that by including the additional 280 mm and 60 mm bases in the process, I have slightly increased the measurement accuracy. For final accuracy, I also used the 60 mm microlevel base at the end of the measurements to perform transverse measurements on the same grid. This provided crosschecks between lines A and B, ensuring a more verified result. After measuring all the points in the scheme and conducting several rounds of measurements with averaged results, I obtained a map of the measured surface. The discrepancies were minimal due to the high-quality measurements. As a result of the conducted measurements, the topography of this surface has been obtained, which was necessary at this stage of creating my straightedge. This map is the first step toward improving the working surface. Now, I will scrape down the elevated areas, knowing their exact locations. The straight edge will become flatter. I will remeasure the new surface and refine it further through scraping and lapping until the surface becomes perfectly flat. I will know the surface is perfectly flat after another similar round of measurements, with deviations at each point reduced to 0. For its intended purpose, the surface will be considered perfectly flat when the error across the working plane is less than 1 micron or 39 millionths of an inch. This is labor-intensive but entirely achievable. I live in Ukraine, and as you may have noticed, I only partially understand English. Please be forgiving of the errors in the text. I hope I can still convey the meaning of my actions to you. If I receive interesting information from you, I will include it in the video description. ChatGPT helps me a lot in editing the text for the video, but it still sometimes, for example, calls a microcator a microindicator or micrometer. Overall, I am struggling to ensure the use of precise terms, so please don't judge me harshly. A straight edge of this quality will complement an autocollimator during surface grinder repairs, and I will achieve the desired accuracy for the machine after its refurbishment. I intend to do everything possible to have a highly accurate surface grinder at my disposal. This will significantly expand my capabilities in future projects, and I hope all of you will witness and be part of this journey through YouTube. I've spent most of my working time this year repairing this machine and simultaneously filming videos about it. In return, I get the opportunity to publish new content on my YouTube channel and receive support from my viewers on Patreon. Perhaps, once the repair is complete, this machine will serve me well, but that remains to be seen. Still, I'm happy to have the chance to create these videos for you. That alone makes it all worthwhile. I still need your support on Patreon, and I am very grateful to those who have already contributed. Your support positively impacts the growth of my channel. Thank you. The Patreon link is in the video description. That's all for today. Thank you for watching, commenting, and liking. Looking forward to seeing you again. Goodbye.